Good day, everyone. We are the third year students, Black D, taking up Bachelor of Science in Civil Engineering. We are here to present to you Chapter 4, which is all about evaporation. There are 6 lessons in this chapter. The first lesson is about introduction and definition. What is evaporation? Evaporation is a type of vaporization that occurs on the surface of a liquid as it changes into the gas phase. Evaporation is one of the three main steps in the global water cycle. It is important or essential part of the water cycle. The sun drives evaporation of water from oceans, lakes, moisture in the soil, and other sources of water. Evaporation of water occurs when the surface of the liquid is exposed, allowing molecules to escape and form water vapor. This water vapor can then rise up and form clouds. With sufficient energy, the liquid will turn into vapor. Evapotranspiration. Evaporation and transpiration involving evaporation within plant stomata.
Hi, I'm Ibsen Mangolabnan and I will uh, present the process of evaporation. So, evaporation is the opposite of condensation. It is the process of the liquid water turning into water vapor. So, when water is heated, it evaporates. The molecules move and vibrates quickly that they escape into the atmosphere as molecules of water vapor. Water is evaporating but staying in the air as a vapor. So, yung water vapor is hindi sila agad-agad tataas dyan sa atmosphere to form clouds. Yung iba is nag-stay sa air which causes humidity. Once water evaporates, it forms clouds. The clouds then release moisture as a rain or snow. The liquid water falls to earth waiting to be evaporated. The cycle starts all over again. So kapag yung water vapor is na-reach na niya na yung appropriate altitude or temperature, it will start to condense in the form of clouds. So, factors affecting evaporation. First is air saturation. If the air is already clogged or saturated with other substances, there won't be enough room in the air for liquid to evaporate quickly. When the humidity is 100%, the air is saturated with water and no more water can evaporate. So if the air is fully saturated, kumbaga, na-reach na yung maximum capacity of air to accommodate water vapor. Air pressure. If air pressure is high on the surface of a body of water, then the water will not evaporate easily. The pressure pushing down on the water makes it difficult for water to escape into the atmosphere as vapor. Storms are often high-pressure systems that prevent evaporation. So, the example, yung storms or yung typhoons uh, na nagkukos ng high pressure which affects the evaporation. Temperature. Temperature affects how quickly evaporates happen. Boiling hot water will evaporate quickly as steam. So, mas mabilis mag-evaporate yung hot liquid compare sa cold. So, factors affecting the rate of evaporation. First, concentration of the substance evaporating in the air. If the air already has a high concentration of the substance evaporating, then the given substance will evaporate more slowly. So, kumbaga yung air is malapit ng ma-fully saturate. Yung evaporation is, rate of evaporation is bababa ng bababa. Over the substance all the time, then the concentration of the substance in the air is likely to go up with time, thus encouraging faster evaporation. This is the result of the boundary layer at the evaporation surface decreasing with flow velocity, decreasing the diffusion distance in stagnant layer. So it means that hindi stagnant yung air. Kaya hindi siya kaagad-agad masasaturate. So there is enough space for water vapor. So the amount of minerals dissolved in the liquid. So nakaka-affect rin yung properties ng pressure. Evaporation happens faster if there is less exertion on the surface keeping the molecules from launching themselves. So sa pressure, meron tayong high and low pressure. 'Di ba doon sa high is for example yun yung storms and typhoons. So mababa yung uh, rate of evaporation doon. But in low pressure, 'di ba yung bagyo is bago siya mabuo is nag-start muna siya sa low pressure. So it means sa area na yon is mataas yung rate of evaporation. Surface area. A substance that has a larger surface area will evaporate faster, as there are more surface molecules per unit of volume that are potentially able to escape. So kapag malaki yung surface of liquid na exposed sa atmosphere or air, is the greater the rate of evaporation. And the last is temperature of the substance. The higher the temperature of the substance, the greater the kinetic energy of the molecules at its surface and therefore the faster the rate of their evaporation. So kapag mas mainit yung substance is mas mabilis siyang mag-evaporate compared doon sa malamig.
Hi, this is Suzanne Rose Titimala, and I am here to discuss the third topic for this chapter, which is the estimation of evaporation. So there are three methods in estimating evaporation. Number one, using evaporimeters. Two, using empirical equations. And three, by analytical methods. So what are evaporimeters? Evaporimeter is an instrument that measures the rate of evaporation of water into the atmosphere and is sometimes called atmometer. So, evaporimeters are pans containing water which are exposed to the atmosphere. Loss of water by evaporation from these pans are measured at regular intervals, maybe daily. Meteorological data such as humidity, wind velocity, air and water temperatures, and precipitation are also measured and noted along with evaporation. So, using these evaporimeters, aside from evaporation, there are also other things na nare-record, which are, yun nga, as mentioned, they are humidity, wind velocity, air and water temperatures. So there are different types of evaporimeter. In our report, we have here 4 types of evaporimeter. Number 1 is USWB Class A evaporation pan. So this pan has a diameter of 1210 millimeter and depth of 255 millimeter. The depth of water is maintained between 18 and 20 centimeter, and the pan is made of unpainted GI sheet. So evaporation is measured by measuring the depth of water in a sealing well with a hook gauge. The pan is placed on a wooden platform, as you can see in the figure, with a height of 15 centimeter ground level to allow free air circulation below the pan. Next is ISI standard pan. This is specified by IS 5973 and known as the modified Class A pan. This pan has a diameter of 1220 millimeter and depth of 255 millimeter. Yung depth niya is same lang dun sa naunang pan, which is the USWP Class A. The pan is made of copper sheet 1.9 millimeter thick, tinned inside and painted white outside. The pan is placed on a square wooden platform, as in the figure, with 1225 millimeter and height 100 millimeter above ground level to allow free air circulation between or below the pan. A fixed point gauge indicates the level of water. Then water is added to or removed from the pan to maintain the water level at a fixed mark using a calibrated cylindrical measure. The top of the pan is covered with a hexagonal wire net of GI to protect water in the pan from birds. Then the presence of the wire mesh makes the temperature of water more uniform during the day and night. Evaporation from this pan is about 14% lower as compared to that from the unscreened pan. Next we have, so yeah, that's the figure. So here it is, yung wire mesh cover, steering well, fixed point gauge. That's the parts of the ISI standard pan. Next, number 3, Colorado sunken pan. This is a 920 millimeter square pan made of unpainted GI sheet, 460 millimeter deep, and buried into the ground within 100 millimeter of the top. So yeah, 92 by 92 centimeter siya. The advantage of using this type of evaporimeter is its aerodynamic and radiation characteristics are similar to that of a lake. However, its disadvantages are it is difficult to detect leaks, expensive to install, and extra care is needed to keep the surrounding area free from tall grass, dust, and others. Next is USGS floating pan. This is a square pan of 900 millimeter sides and 450 millimeter deep. It is supported by drum floats in the middle of a raft of size 4.25 meters by 4.87 meter. It is set to afloat in a lake with a view to stimulate the characteristics of a large body of water. So yan, as you can see in the figure, the USGS floating pan is on the lake. The water level in the pan is maintained at the same level as that in the lake, leaving a rim of 75 millimeters. Diagonal baffles are provided in the pan to reduce surging in the pan due to wave action. The disadvantage of using this type of evaporimeter is that it requires high cost of installation and maintenance, and it is difficult in making measurement. So we have discussed yung types of evaporation pans. However, evaporation pans are not exact models of large reservoir. Therefore, so one, they differ from reservoir in heat storage capacity and heat transfer characteristics from the sides and the bottom. The height of the rim in an evaporation pan affects wind action over the water surface in the pan, and it casts a shadow of varying size on the water surface. And the heat transfer characteristics of the pan material is different from that of a reservoir. Therefore, evaporation measured from a pan has to be corrected to get the evaporation from a larger lake under identical climatic and exposure conditions. Dahil dito, we calculate the lake evaporation by multiplying the pan coefficient and the pan evaporation. So in this table, we have the values of pan coefficients, the different types of pan are Class A land pan, ISI pan, Colorado sunken pan, USGS floating pan. So yung average nila is 0.70, 0.8, 0.78, 0.8. So based on this table, ito yung kanilang mga pan coefficients. So kapag magkakalculate tayo ng lake evaporation, we need this data. So WMO recommends the following values of minimum density of evaporimeters. Okay, with WMO is the World Meteorological Organization. So for arid zones or yung land with no to little rain, it requires one evaporation station for every 30,000 square kilometers. Sa humid temperate zones naman, it needs one station for every 50,000 square kilometer, and on cold regions, one station for every 100,000 square kilometers. So an evaporation station, a typical hydrometeorological station has the following. First is recording rain gauge and non-recording rain gauge. So the top photo is a recording rain gauge, while dito sa baba is a non-recording rain gauge. Next is a Stevenson box with maximum, minimum, wet, and dry bulb thermometers. So a Stevenson box, as you can see in the photo, is a double louvered wooden box painted white, and it is specially designed to shield the thermometers from the direct rays of the sun, from precipitation, and from heat radiation from the ground. This box allows, or yung pagka-construct niya na louvered construction, yan, as you can see, it allows the free flow of air over the thermometer bulbs. Okay, inside this we have maximum, ito sa top, maximum thermometer, minimum, then dry bulbs and wet bulbs. Next, we have wind anemometer and wind vane. Yung nasa taas is this part is anemometer, and nasa baba is wind vane. Yung a cup anemometer is like it starts spinning when the wind blows from any direction. So as wind speed increases, the anemometer also spins faster. So parang anemometer is sa wind speed siya. Yung wind vane naman, however, is it points to the direction where the wind is blowing. So yung shape niya, it will be pointed this northwest, east, south. It points to the direction where the wind is blowing, and it can rotate freely to indicate any direction. Last, we have a sunshine recorder. Sunshine recorder is a meteorological instrument which is used for recording the amount of sunlight that a particular location receives throughout the day. So sa loob niyan, it has a paper strip and a glass sphere that focus on sunlight strongly enough to singe the paper. So yung result from this recorder, it provides information about the weather and climate as well as the temperature kasi nga it records the sunshine. Now, moving on to the second method of estimating evaporation, we have by using empirical equations. So most of the available empirical equations for estimating lake evaporation are a Dalton type equation of the general form EL equals K times F of U times EW minus EA. So EL here is lake evaporation measured millimeter per day. EW is saturation vapor pressure at the water surface temperature measured millimeter of mercury. EA equals actual vapor pressure of the overlying air at a specific height millimeter of mercury. F of U is the wind speed correction function. K is the coefficient, and EA is measured at the same height at which wind speed U is measured. So we decided to do a separate video about this and provide sample problems and provide solution using these equations. So we have next Mayer's formula. It is the empirical equation used to determine the lake's evaporation. So the formula is flashed on the screen. Next, we have the rower's formula. This accounts for the effect of pressure in addition to the wind speed effect. So the formula is given. Next, we have the third method of estimating evaporation. It is by using analytical methods. We have three analytical methods. One is water budget, two is energy budget, and three mass transfer. The first one is water budget method. This is the simplest but the least reliable. So the formula is daily precipitation plus daily surface inflow into the lake plus daily groundwater inflow is equal to daily surface outflow from the lake plus daily groundwater outflow plus daily lake evaporation plus increase in lake storage in a day plus daily transpiration loss. So all quantities are expressed in units of volume or depth. Next method is the energy budget method. It involves application of the law of conservation of energy. Energy available for evaporation is determined by considering the incoming energy, outgoing energy, and the energy stored in the water body over a known time interval. Estimation of evaporation from a lake by this method has been found to give satisfactory results with errors of the order of 5% when applied to periods less than a week. So, the formula for energy budget method: the net heat energy received by the water surface equals sensible heat transfer from the water surface to the air plus heat energy used up in evaporation plus heat flux in the ground plus heat stored in the water body plus the net heat conducted out of the system by water flow. So the heat energy HE is equal to PL EL, which is EL is evaporation, L is latent heat of evaporation, and P is the mass density of the fluid. You just multiply the three and you find HE. So this is the figure of illustrating the energy balance in a water body. So this is the energy balance in a period of 1 day. All energy terms are in calories per square millimeter per day. If time periods are short, HS and HI can be neglected as they are negligibly small. All terms except HA can either be measured or evaluated indirectly. HA is estimated using Bowen's ratio, wherein beta equals HA over HE equals to that value. So beta equals HA over HE is equal to 6.1 times 10 raised to negative 4 times atmospheric pressure times the quantity of temperature of water surface minus temperature of air all over saturated vapor pressure minus actual vapor pressure. So the comparison of the methods. Analytical methods can provide good results, however, they involve parameters that are difficult to assess. Empirical equations can at best give approximate values of the correct order of magnitude. In view of the above, pan measurements find wide acceptance in practice. So as I've mentioned earlier, we are going to provide a separate video like solving problems and using the mentioned methods. Now let's proceed to the fourth topic of this chapter, which is evaporation from different surfaces. It is said that all liquids evaporate if exposed to certain elements. The rate at which a liquid evaporates depends on its molecular structure. The other factors that affect evaporation are surface area, temperature, and air movement. So these are already mentioned on the second part, which is the factors affecting evaporation. So testing the effect of surface area. Molecules contained in a liquid evaporate from the surface area, and this means that the larger the surface area, the faster the rate of evaporation. To prove this, we have an example experiment. First, we need two different containers and we must put water in it. The first container must have a diameter of 3 or 4 inches, such as glass, and the other one must have a diameter of 8 to 10 inches, such as bulb. So It is noticeable that one container is larger than the other. So next step is to put 2 ounces of water into the measuring jug, then transfer it to the glass. Do the same for the bowl and then place the containers next to each other. This means that all other factors that affect the rate of evaporation are identical. So they put the same amount of water sa dalawang container which have different surface area. So leave the containers for 1 hour. Then pour the water from each container into the measuring jug and write down how much water is left. So in this experiment, we're going to find out that the amount of water left in the bowl is much less than is left in the glass due to the difference in surface area. So in conclusion, the rate of evaporation is faster when the surface area is larger.
Hi, my name is Adam Fidencio Sorena, and this is the components of evaporation from vegetation covers. Evapotranspiration is the sum of evaporation from the land surface plus transpiration from plants. It is the water lost to the atmosphere from the ground surface, evaporation from the capillary fringe of the groundwater table, and the transpiration of groundwater by plants whose roots top the capillary fringe of the groundwater table. The transpiration aspect of evapotranspiration is essentially evaporation of water from plant leaves. Studies have revealed that transpiration accounts for about 10% of the moisture in the atmosphere, with oceans, seas, and other bodies of water providing nearly 90% and a tiny amount coming from sublimation. The figure shows the typical plant, including any found in a landscape, absorbs water from the soil through its roots. That water is then used for metabolic and physiologic functions. The water eventually is released to the atmosphere as vapor by a plant's stomata, a tiny closable pore-like structures on the surface of the leaves. Overall, this uptake of water and roots, transport of water through plant tissues, and release of vapor by leaves is known as transpiration. Water also evaporates directly into the atmosphere from soil in the vicinity of the plant. Any dew or droplets of water present in stems and leaves of the plant eventually evaporates as well. Scientists refers to the combination of evaporation and transpiration as evapotranspiration, or ET. Transpiration, the release of water from plant leaves. Just as you release water vapor from when you breathe, plants do too, although the term transpire is more appropriate than breathe. This picture shows water vapor transpired from plant leaves after a plastic bag has been tied around the stem for about an hour. If the bag had been wrapped around the soil below it, too, then even more water vapor would have been released, as water also evaporates from the soil. Plants put down roots into the soil to draw water and nutrients up into the stems and leaves. Some of this water is returned to the air by transpiration. Transpiration rates vary widely depending on weather conditions, such as temperature, humidity, sunlight availability and intensity, precipitation, soil type and saturation, wind, and land slope. During dry periods, transpiration can contribute to the loss of moisture in the upper soil zone, which can have effects on vegetation and food crops. fields. How much water do plants transpire? During a growing season, a leaf will transpire many times more water than its own weight. An acre of corn gives about 3,000 to 4,000 gallons of water each day. A large oak tree can transpire 40,000 gallons per year. Transpiration and groundwater. In places where the water table is near the surface, such as next to lakes and oceans, plant roots can penetrate into the saturated zone below the water table, allowing the plants to transpire water directly from the groundwater system. Here, transpiration of groundwater commonly results in a throwdown of water table, much like the effect of a pumped well.
Lesson 6 is about progress in understanding evaporation processes. Evaporation is the process of a substance in liquid form transitioning into the gas phase. For evaporation to occur, the liquid must gain enough energy to excite the molecules to move farther apart. Often, the energy comes from heat. Evaporation in the atmosphere. Water molecules are constantly cycled through our atmosphere when rain falls, then dries up and eventually falls again. When the various sources of water on the planet dry, evaporation is occurring. Evaporation in daily life. Evaporation commonly occurs in everyday life. First example is when you get out of the shower, the water in your body evaporates as you dry. The second one is if you leave a glass of water out, the water level will slowly decrease as the water evaporates. And another important example of evaporation is sweating. The sweat requires energy to evaporate off of your skin. It gets that energy from the excess heat your body is producing, in turn, causing you to cool down. These are other examples of evaporation in everyday life. Thank you for watching. And we are the group for Black D.